Hello, welcome to Mr. Boyce's 2025 midterm review. If you are watching this and you are not in my class, then wow, go you for being an overachiever. Feel free to stop by my room if you'd like a blank copy of this review. For those of you in my class or anyone really, please make sure you do the review first. So I'm going to be giving answers in a range, not the actual answer. Your assignment obviously will require that you have the actual answer. But if you have a good range, then you know if your answer is correct or not. Some things I'm just going to have to give you the answer. So really, it's important for you to do this first. This is the best time to make a mistake now versus on a test. So with that over, let's go ahead and get started. First question, what is a formula for iron 3 carbonate? So remember iron is a variable charge. So we don't know what the formula is unless we figure it out from, the charge, unless we figure it out by looking at the formula and seeing, say, for example, it went 1-to-1 with oxygen, then that would have been iron 2. Or reading it from the name, in this case, it's saying iron 3. So iron with a +3 charge, and carbonate. Now, carbonate, that doesn't end with an ite, so that sounds a bit like a polyatomic to me. Let's see if we can find that. Okay. Carbonate, and there it is, bingo, carbonate. CO3 with a -2 charge. That charge is very important. So CO3 -2, and you want to think of the polyatomic as being one thing. So we're going to swap drop and reduce these charges. No reduction necessary, but this is going to be Fe2, and then CO3 stays together, and we want 3 of those. So that's going to be your formula. Okay, what is the name of the compound Fe2SO43? That's a pretty big compound, but we already know Fe is iron. Okay, and SO4, well, that looks like a polyatomic again. So what is SO4? Let's see. Here we go. Sulfate, not sulfite, sulfate. And that's got a -2 charge, which is going to be important for us to remember that this has a -2 charge. So SO4 -2 is sulfate. Let's go back to where we were. Okay, and sulfate, SOO4 -2, and iron. Now, if we reverse swap drop, basically, uh, this has got a 2 here, so we're going to move that 2 up there, which is good because that is a -2. And I'm going to reverse swap drop here. So that would mean that this must have been a +3. That's what's going to go together in that ratio. Okay, if you look at that and do a swap drop again, so this iron must have been a +3 charge, which it was. So this is iron 3 sulfate. Okay, the number of atoms in 0.75 moles of aluminum. So we are wanting the atoms and we have moles. So this looks like a one step. That's nice. So 0.75, start with what we know. Moles of aluminum. And the first thing I'm going to do before I even think about what to do next is to move my unit down. That's where it belongs. Moles of aluminum. And I want atoms. All right, probably shouldn't cross it out, maybe just underline it. I want atoms, and 1 mole of aluminum or anything else is composed of 6.02 times 10 to the 23rd, in this case, atoms of aluminum. Okay, and since the one's on the bottom, I'm going to multiply. So let's take a look at this. This is question number 3 on my calculator here. First thing I'm going to do with the calculator when I first start to use it is I'm going to clean it out just in case somebody put some weird settings in there. So I'm going to go ahead and do second 0 to reset it. And now that it's cleared, I'm feeling a little more comfortable with it. So 0.75 times And we got to put in Avogadro's number. So that's 6.02. Oops, it didn't give me a 6. That's not good. 0.75 times 6.02. And then times 10 to the, I like to use the function. See if you can sort of see this 10 to the down here. So second log, that brings that up 23. See, I'll have two parentheses, so I want to close them both and then hit enter. And I've got 4.515 times 10 to the 23rd. So I'm going to round that to, if not, then somewhere in between, your answer will be around 425 times 10 to the 23rd. 4 to 5. Remember, this is a range I'm putting on these. I do want you to try and solve it yourself and see if your answer is somewhere within that same range. Next, how many grams of water are present in 4 moles? Okay, well, let's go ahead and get started. Oops. Okay, so I'm going to start with what I know, and that's 4 moles. Okay, first thing to do, as always, is bring my unit down, and I want to convert to grams. I can do that in one step. Okay, and 1 mole, if I want to know how much 1 mole of water weighs, I'm going to add together the molar mass of 1 oxygen and 2 hydrogens, which comes out to just about 18. And so your answer should be, when you put it in your calculator, 4 times 18 is between 70 to 75 grams of H2O. So there's your answer. Okay, if 0.5 moles of a substance weighs 10.4 grams, what is the molar mass of that substance? Okay, so in other words, I have 0.5 moles. And remember, a mole, the molar mass, refers to 1 mole. So if half a mole is 10.4 grams, then how much would a full mole be? Well, twice that. So okay, 10.4 grams, all right, times 2 equals right about 20 grams. Okay, find the percent composition of nitrogen in ammonium nitrate, and it gives you the molar mass of ammonium nitrate, which that's nice, because then you don't have to figure it out yourself. So cool. Percent composition, just like most fractions, is part over whole. So you want part over whole times 100. Okay. And remember, this formula is in your periodic table formula sheet too. Now, I want to know nitrogen. Well, and for nitrogen, I have one here, but I also have one here. So I have 2 nitrogens. It's important to notice that. So I am going to do, oops, part over whole, which is going to be N times 2 divided by, and I already have my molar mass, so 80.04, and 2 nitrogens is going to be 14 times 2, so 28 divided by 80.04. And when you put that in your calculator, that should be somewhere around 0.320 to 0.4, or about 30 to 40%. Okay, so what is the percent composition? of oxygen and calcium carbonate. Well, we're going to have to do a little effort here. We're going to have to look this stuff up. So calcium carbonate, I've got calcium, which always has a +2 charge, and I want carbonate. So let's take a look here. So there's my calcium. Remember, these are all +1, +2, +3, and then these are -1, -2, and -3. And carbon and silicon can kind of go both ways, but they're not very common in ionics. So, all right. So what I wanted was calcium carbonate. So here's calcium, which has a +2. And let's see if we can find carbonate somewhere. Oh, there it is. We already found it once today. And that's a CO3 with a -2 charge. So let's get back to where we were. Okay, and so Ca +2 and CO3 -2. So this can go together in a 1-to-1 ratio. Swap drops my 2's, 2 to 2 is the same as 1 to 1. With an ionic, we do want to reduce those. So that's going to be CaCO3. Okay, and I want percent composition of oxygen. So that means I've got O3 divided by CaCO3 and 3 oxygens, 16 apiece. That's going to be about 48 divided by 100. Okay, and so that's going to be right about close to in the area of 0.45 to 0.55. So somewhere around 50%. Okay, what is the percent compositions of all the elements in H2O2? We would call that dihydrodioxide, but in the grocery store, you would call that hydrogen peroxide if you are in the know. So let's take a look. First, we have hydrogen and we have oxygen. And so hydrogen is going to be H2 divided by H2O2, and oxygen is going to be O2 divided by H2O2. And so that's going to be 2 divided by 34, because that's the weight of 2 oxygens and 2 hydrogens combined. And 2 oxygens would be 32 divided by 34. So as you can see, this is mostly oxygen, as the oxygen is much bigger. And so that's going to be about 0.05 to 0.06, somewhere in that range. And this is going to be about, about 0.92 to 0.96, somewhere in that area, which would be about 5% over 95%. Again, trying not to give the exact answers with this because it's very important to me that you do work these out yourselves and not just watch. It is helpful, but it also brings a lot of what's called confirmation bias. You can see me do this and say, oh, that looks really easy. And I believe it would be very easy for you too if you were doing the same problems for years, several times a day. But you don't have quite that much time to study. So make sure you're doing these on your own, please. All right. Calculate the molarity of a solution containing 10 grams of NaOH dissolved in 500 milliliters of water. All right, so now we are going to kind of a different formula. We want molarity, and molarity equals moles divided by liters. So it's very important that you have it in both moles and liters. And grams is not the same thing as moles. We can get there, but it's not good yet. So 10 grams of NaOH. Okay. And so grams of NaOH. And I want to convert that to moles. So mole NaOH. And that's good. I can do that. So if I add together the molar masses of a sodium, an oxygen, and a hydrogen. And I put all that together, it's going to be right about 40 grams. And so 10 divided by 40 is about a quarter, 0.25 moles. Okay. And 500 milliliters, that's not a liter, right? There's 1,000 milliliters in 1 liter. So 500 is going to be 1/2 or 0.5 liters. But now that I've got both liters and moles, since molarity equals moles over liter, I can do this at 0.25 divided by 0.5. Okay, and that's going to come up to right about 0.4 to 0.5 molar. Actually, let's change that. About 0.5 molar. Okay, if 50 milliliters of a 0.5 molar solution is diluted into a final volume of 200 milliliters, what is the new molarity of the system? Well, very first thing I want to do is I want to rewrite the equation. This is just me, but I think especially in this case it helps. So this is how we do a dilution. Now I'm starting with if 50 milliliters, and so I get a volume, okay, and a molarity is diluted into a final volume. So I have another volume. What is the new molarity? And so this would be your 2. This would be what you start with. And this is what I want to solve for. So if I want to solve for M2, then what I'm going to do is go ahead and divide both sides by V2. And that will let V2 cancel on this side. So my newly rewritten and much easier equation is M2 equals M1V1 divided by V2. Now, keep in mind, we have to have molarity and we have to have liters. So M1, is that good? It is. So we can put 0.5 times, and my V1 is 50 milliliters. Is that going to work? No, it is not. So let's go ahead and figure this out. 50 milliliters, bring our unit down, and what we want, and 1 liter is equal to 1,000 milliliters. And so if I divide 50 divided by 1,000, that comes out to 0.05 liters. Okay, and my V2 is 200 milliliters. So I'm going to put that through the exact same thing, but instead of 50, I'm going to have 200. Remember, our conversion factors should work no matter what number we're using for our math. And if I put 200 in there, I'm going to get 0.2 liters. Okay. Okay, and in my calculator, if I put together 0.5 times 0.05, divide that by 0.02, then I am going to end up with about roughly 0.1 to 0.2 molar. So if your answer is between 0.1 and 0.2, congratulations, you were correct. How much water should be added to 100 milliliters of 6 molar hydrochloric to make a 1 molar solution? So that's good. We don't want it to be that strong, so let's cut it down just a bit. M1V1 equals M2V2. And again, I want to write this out correctly. So this is going to be my V1 and my M1 and this is going to be my M2, and therefore what I want is my V2. So let's put that correctly. So V2, let's rewrite it. So V2 is equal to M1 V1 divided by M2. All right, so let's see. What do I have listed as M1? I have that at 6. That's good. We don't need to do anything to that. And my V1 here is 100 milliliters. This is super common, guys. In the lab, our graduated cylinders pretty much only measure in milliliters. And so liters is not very practical for in lab, but it is needed for this formula. So 1,000 divided by 100. Just remember, you can just move the decimal places over 3, and that's what I'm going to do. So times 0.1. So 6 times 0.1. And then we're going to divide that by our M2, which is already in molarity. So that's divided by 1, which we all know means divided by 1. It's just going to be 6 times 0.1, which you can probably guess the answer, but I'm still going to write it as a range just in case someone's reading through answers only. And so it's somewhere between 0.5 to 0.65, somewhere around there. Liters. Now, or roughly, okay. And if I wanted that in milliliters, then I would just multiply that number by 1,000. So that would be somewhere between 500 and 650 milliliters, somewhere around there. 13, another one of these, big surprise. So let's rewrite this. M1 V1 equals M2 V2. And we want, in this case, we want V1. So V1 equals, divide both sides by M1. And I've got M2 V2 divided by M1. Okay, and so let's figure out what those are for number 13. So we have our M2 is 3 molar times 0.25 liters. Remember, 250 milliliters, we got to change that. And then we're going to divide that by 9 for 9 molar. Okay, and if I put that into my calculator, that's going to be somewhere around 0.08 to 0.09, somewhere around there, which would be about 80 to 90 milliliters if you convert that for your answer. Okay, 14. All right, let's look at a different way of solving this, just in case you want to try. If you don't want to rewrite the formula every time, although I highly would not recommend it. M2 V2 for this one, what we can do is we're solving for V1, because I want to know how many milliliters of a solution there's going to be. Now, again, I do absolutely have to convert between milliliters and liters in order for this to work. If you Google this, you may see something called millimoles, but I'm not teaching that as a concept, but it would work if you happen to find that. But anyway, let's get back to what we're doing. And so that's going to be M1 is 2 molar times X equals 0.4 times 0.1. So on a 0.4 molar solution with 1/2 of a liter or 500 milliliters. And if you want to solve it this way, then you can solve for X. And so X is going to equal somewhere around 0.06 to 0.1. So right about there. 0.01, of course, would be like 100 milliliters. Whew, okay, on to something new. Determine if the following compounds are ionic or covalent and name them. So first thing we want to do, are they ionic or covalent? This is Na, a metal, and Cl, a non-metal. So make sure you were looking at your periodic table here. And remember this stair step here for metal versus non-metal. And Na, and I won't do this for all of them, but just kind of pointing this out. So I have a metal and a non-metal. I got a +1 and a -1. So these are going to go together 1 to 1, which they do. Great. And so for this, I'm going to call this ionic. Okay, and we're going to call that sodium chloride. So this is a monoatomic, so I'm going to change chlorine to chloride. If it was a polyatomic, I would just leave the name of the poly. CO2, this is two nonmetals, carbon and oxygen. And so this is going together as covalent. And for covalent, you, unlike ionic, where you have charges and you swap, drop, and reduce, and sometimes you have a variable charge, but either way, it still only has one way it can go together depending on its charges. Covalent doesn't do that. Covalent shares. Covalent has all kinds of different ways they can go together. So if you don't tell us how much is in there, there's no other way to know what it is you're talking about. So we do use things like mono and di, tri with covalence. And so I have one carbon, so that's going to be carbon. Now you don't use mono if there's only a first one. If you forget about that, think of something you know, like monoxide, or I'm sorry, carbon monoxide. That's a dangerous gas. It would sound weird if you said monocarbon monoxide. It's just not how it works. So carbon, in this case, we have two oxygens, so carbon dioxide. And you probably heard of that one too. Ooh. Come back. Carbon dioxide. Now, H2O. Well, I mean, first off, we can tell this is all nonmetals, so we know this is covalent. Well, that's being lazy. Let's just write it. Okay, and so yeah, we know that's water. That one's fair enough. Uh, but what we call this in our class right now with our naming rules, and we would call that dihydromonoxide. So notice I do use mono for the second one. So stay hydrated, drink plenty of dihydromonoxide, be healthy. All right, calcium and oxygen. Well, calcium is a metal and oxygen is a non-metal. Okay, and so we're going to call that calcium oxide. NH3, non-metals. Okay, so this is ionic, covalent. And I have one nitrogen and three hydrogens, so I'm going to call that nitrogen trihydride. So remember, we still use the ides. So nitrogen trihydride. If you were to go to a grocery store and look for this, they would call this ammonia. So there you go. Okay, what are some of the big differences that we need to know between ionic and covalent compounds? Well, there are some pretty big differences. First off, let's see. ionic versus. So what are some big things to remember about these? First off, ionics transfer electrons, whereas covalent share electrons. So they're both trying to get to that octet, but they do it in different ways. When you transfer electrons, you create a charge which is called an ion, and that ionic charge is what creates the bonds, hence the word ionic charge. Covalent, as in co-sharing valence electrons, they will share to get to an octet. All right, what's different? So ionic will break into positive and negative ions so they can conduct electricity. Versus covalent, which cannot. Okay. How about something else? Let's see. Ionic is a metal plus non-metal, and covalent is non-metals only. And a metal plus a non-metal will also include polyatomic ions. So there is a situation where there could be two polyatomic ions, like ammonium nitrate or something like that. In that case, there wouldn't actually be any metals there, but it would be two polyatomic ions, hence the name ion, and it's going together because of their ionic charges. Kind of a rare case, but it is something you should know. Okay. Okay, molar mass of sulfuric acid. So in this case, we went ahead and just gave you the formula, but remember your acid naming rules. If it's you ate and got sick, so if the polyatomic ion ends in ate, like sulfate or something like that, then all acids start with hydrogen. So hydrogen, or enough hydrogen is needed to balance out sulfate, would turn into sulfuric acid. For say sulfite, all right, hydrogen plus sulfite. So ite turns into OUS, so that would be sulfurous acid, and hydrogen with just a monoatomic is equal to blank. Oops, sorry. I was forgetting something. Hydro blank ic acid. So if this was just hydrogen and sulfur, like not a polyatomic, then hydrogen hydrosulfuric acid. Okay, in this case, this is sulfate, and you ate and got sick. So this is sulfuric acid. That's a bit of a side note. It's actually asking us for the molar mass. So let's just go ahead and get onto that. And that's going to be hydrogen times 2. It's going to be sulfur times 1 and oxygen times 4, right? Which is going to be 1 times 2 plus 32 plus 16 times 4. Okay, which is 2, oops, 32 and 64. And we're going to add all of those together, and that's going to be about 90 to 100 grams per mole. A sample of compound has a mass of 18 grams and contains 0.1 moles of the compound. What is the molar mass of the compound? Okay, so if 0.1 moles equals 18 grams, then 1 mole equals 18 times 10. In other words, the difference between 0.1 and 1. And so that's going to be kind of hard to give a range because that one's a little easy. So 180 grams per mole. Explain the difference between saturated, unsaturated, and supersaturated solution. Okay, well, hope you're not going anywhere. So saturated equals cannot, whoops, dissolve any more. So that's when you've reached the point you've dissolved as much as you can dissolve at that temperature. Before you get there, you would be unsaturated. And that means you can dissolve more. Or supersaturated. And that means more solute. Dissolved than should be at current temperature. So in other words, here's my chart. Let's take a look. Everyone see this? So let's look at KCl here. Okay. Now, if I were to at, let's say, 50 degrees Celsius. Ooh. Let's say at 50 degrees Celsius, I want to dissolve 60 grams of solute. Then that is going to meet right here. And that would be supersaturated because this is above the saturation line. The saturation line at 50 degrees is right here, and that's just a little over 40, so 42, something like that maybe. And anything less than that means that you can still, at the current temperature, dissolve more, so therefore it is unsaturated. So make sure you can see that on a chart. You will have some questions like that. Okay, if I add more solid to a saturated solution of salt water, what will happen? And that is the solid not dissolve. Dissolve will stay solid. So basically, it's just going to clump around at the bottom. Okay, and how can we create a supersaturated solution? And that is dissolve solute at high temp and forgetting how to spell cool. Okay, so basically what that means is, let's go back to KCl. Let's say I heated that thing up to 80 degrees, which would allow me to dilute a little more than 50 grams. If I do that and I cool it down, let's say here to 40 or something like that, then 50, this is in the supersaturated range. Yeah. Okay, number 22, referring to solubility curve, at what temperature is the solubility of NaCl 40 grams per 100 milliliters of water? So first thing I want to do is take a look here at my chart. Let's just go ahead and clean it up. Okay, and one thing to note that water weighs exactly 1 milliliter per gram. So 100 grams of water is the same as 100 milliliters. Uh, okay, at what temperature? It'll be 40 grams per 100 milliliters. So here's 40 grams, and let's find NaCl. So here's NaCl, and we want 40 grams. So let's just follow that along until we see it hit 40 grams, which is right about here, which is 90 degrees. Let's move that up a little more. Okay. And this one's a little hard to read, kind of a flat line, so probably wouldn't be a good choice for a test question. But let's just say it's going to be somewhere right around 80 to 90 degrees Celsius. Okay, at what temperature is the solubility of KNO3 90 grams per 100 milliliters of water based on the solubility curve? So KNO3, let's find that one. All right, let's just pick a different color. Why not? Okay, and what we want to know is at what temperature. And so this temperature, it looks like it might creep just a little bit past 50. So we're going to say somewhere between, 50 to 55 degrees Celsius, somewhere around there would be fine. Hey, remember, you do need to have more specific answers, but in this case, exactly specific is a little hard to get since you're reading the chart. Okay. Okay, 24. A solution of sodium chloride contains 10 grams of NaCl. Dissolved in 100 milliliters of water. What is the molarity of that solution? So if you will recall, molarity equals, molarity equals moles over liters. So we need to find out, do we have moles and liters in here? And we do have 10 grams of NaCl, and we have 100 milliliters of water. And so first thing we want to do is convert 10 grams of NaCl. This looks familiar. Did we already have this question? Maybe. Okay, and if you add up one sodium and one chlorine, that's going to be 58.44 grams for 1 mole. So remember, take your unit grams. Whatever goes up must come down. I want to convert that to moles. I can do that. 10 divided by 58.44 comes out to 0.17. Whoops. Mole. Be careful if this is a multiple choice, almost for sure 0.17 is going to be one of your options, but they didn't ask you how many moles, they asked you what is the molarity. Very different, and that's moles over liter. 100 milliliters is equal to 0.1 liters if you divide that by 1,000. So just really make sure you know that it's 1,000 milliliters for every liter. It comes up a lot. Okay, and so 0.17. What? Why do I keep on and write it like that? 0.17 moles divided by 0.1 liters is going to equal between 1 to 2 molar. So make sure that you find the actual answer, and it will be between 1 and 2 molar. If that's what you got, congrats, you did good. Okay, halfway. We're getting there. We're making some progress here. All right, so halfway through. Let's see, 23, 24, 25. Okay, if you reach the saturation point of a solution, what would you expect to happen if you decrease the temperature of the solution? There are two possibilities. So possibility number one is solution becomes supersaturated. However, becoming supersaturated isn't like a guarantee. Not every solution is able to do that. So, like sugar is really great at doing it in water, which is how we can make sweet tea, but not everything does it. So, another possibility could be that the solute falls out of the solution. And if that happens, then it's just going to start forming a solid on the bottom. Oh, okay. Now we made it to part two. Let's go ahead and get started with that. Okay, first question, rank the elements from largest to smallest ionization energy. So BaO, Ca, and Ni. So first thing we do, this will be a little easier using a periodic table. So let's do that. Periodic table, and I'm going to clean this up because I already answered it once and I'm redoing it. Okay, so first off, let's take a look at what we have, what we want to find. So we want to find barium, there's it is. Oxygen's right here, calcium's here, and nickel's right here in the middle. This is one of our transition metals. And so let's talk about ionization energy. You may remember we did first, second, and third ionization energy, but for this question, we just really need to worry about first ionization energy or just ionization energy. This is the amount of energy it takes to basically turn something into an ion, to remove the outermost valence electron. So we want to think about which ones are easier, which ones are harder to remove electrons from. And here, these all form -1, -2, -3. So these are trying to gain an electron. They're already pretty close to having an octet. So it's not very likely you're going to get an electron from those guys. Here, group 1 and 2 are a +1 and a +2. So they're going to be a bit easier. So also when it comes to the trend, we have radius 1, 2, 3, 4, 5, 6. And as we go down, we keep adding energy levels and we're getting bigger and bigger and bigger, which makes it harder to hold on to our outer valence electrons. So the trend is going to be right here. This is going to be the hardest to remove from. It's already got 7 and it only has 2 energy levels and the fewest number of, the most protons you can have with only 2 energy levels. So this is small and strong and it's holding on to its valence electrons and it's going to try and attract more. So you're not taking them away. And then our trend, we're going to go this way down to francium. And francium has 7 energy levels. It's nice and chunky. It's only got 1 valence electron, so it's trying to lose them. So as you can imagine, the energy required is a lot less. So following our trend line, it's pretty obvious that oxygen is going to be the most electronegative and therefore require the most ionization energy, followed by nickel. And then we have calcium and barium, which are in the same family, the +2. So we can't just go by charge. In this case, what we're going to do is we're going to rank them by their radius. And barium has 6 energy levels and therefore larger than calcium. So it's going to require less energy. So in order of the most energy, it's going to be oxygen, followed by nickel, followed by calcium, and then finally barium would have the lowest ionization energy. Okay, and for that one, so that's a little hard to just write all that down, I'm going to say C video. Okay, and here on mine, this is corrected. I corrected it on your worksheet, but I want to compare Moseley and Mendeleev, two early pioneers of the periodic table. Both are pretty awesome. And what are a few differences? Well, Mendeleev, he kind of came first. He's a Russian scientist, and he noticed that there were periodic changes in attributes for atoms, hence the word periodic table. And he grouped them, so Mendeleev grouped them in triads, in other words, groups of 3, And a very important thing about Mendeleev is he also ordered things ordered by mass. Okay. And if you look at the periodic table, now our periodic table is arranged by atomic number. This is the number of protons. And as you know, the number of protons is what identifies an atom. For example, carbon has got 6 protons. And so it doesn't matter how many neutrons or electrons it has. If you have 6 protons, you're carbon. If you have 7, you're nitrogen, and so on. And so this became a better way to arrange that. So Moseley is known for arranging I probably spelled that wrong, table by atomic number, which is what we do now. Okay. So when an atom becomes an ion, it gains a positive or negative charge. How does this affect? Yeah. How does this affect the radius for both positive and negative? Well, for positive, this equals, remember, electrons are negative. So as weird as it sounds, losing electrons makes you more positive. All right. And so if you lose an electron versus negative equals gaining an electron. Now, when it comes to radius, you have all these negative charges kind of outside there in your valence electrons. It seems intuitive that adding an electron is going to make something bigger. And thankfully, that is sort of the case here. But remember, that's not because of the mass of an electron. The mass of an electron is pretty much negligible. It's like 1/2000th that of a proton. So what's really happening here is these negative charges are pushing each other away. Right? So they're repelling each other. So as I add more negative charges, if I put another one in there, then they are going to repel each other. And therefore make a larger radius. So it's kind of important to know the difference between those, and it makes a huge difference. So if you are ranking things by radius, generally an anion, which is a negative ion, is going to be much smaller than a cation, which is a positive ion. So gaining and losing electrons has a big effect on radius. Okay, next, let's draw the Lewis structure for CO2. So we're into something new. So step 1 is to count your valence electrons. So carbon and oxygen, and carbon, I have 1 carbon, so that's 4 valence electrons, and oxygen, I have 2 oxygens, all right? And each one has 6, but I have 2 of them, so that's going to be 6 times 2, or 12 valence electrons. So that makes my magic number 16. I have 16 electrons, no more, no less, and I have to draw this with it. So the next step is to draw it simple, and don't stop there. That's not where we end. It's best to write these in pencils. So I'm going to draw it simple. Carbon can make 4 bonds. It's the most electronegative. I've got 1 of those and 2 of everything else. So I'm going to put it in the center and draw it simple. Now remember, anytime you have a bond, that's going to be 1 electron from one atom and 1 from the other. So this is going to cost 2 electrons. Every time I draw a stick, that's 2 electron charge, and I drew 2 of them. So this is -4. Okay, so I've got 12 electrons remaining. How am I going to spend those? Well, my next step is to start giving octets. They will fill up everything on the outside. So I'm going to start here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But this doesn't work for carbon. So for now, my oxygens are both good, and I'm out of electrons. I've used all 16 of them. I can't use any more for the center. And so if I don't have enough electrons to fully make an octet, then what I'm going to do is start sharing them And so in this case, I'm going to take this pair away. Okay, and I am going to have oxygen share. Now this is fine because it still has 1, 2, 3, 4, and then 2 bonds. So 5, 6, 7, 8. So we have our octet taken care of at 8 for the oxygen. And now carbon is getting closer. It's got 6. So it's not quite enough. We're getting close, but we're not quite there. And so what I'm going to do is just do the same thing on the other side. And wow, I'm going to have to erase more than I wanted to. Okay, so let's just get rid of that. And I'm going to turn this into a double bond as well. So now everything is taken care of. Everything's got 8 valence electrons, and I use 16 electrons to do it. Okay, HOCl, and remember chlorine is not a carbon and an iodine or something. That's Cl. A little hard to tell when it's typed that it's a lowercase l. So I've got HO and Cl. I have 1 of each. So 1 valence, 6, and 7. So that's going to equal 14 electrons. I'm going to draw it simple. Now between hydrogen, oxygen, and chlorine, let's take a look here at our periodic table. Kind of a quick way to look at this is how many times do they need to share to get to an octet? So an octet for most everything is 1, but hydrogen is only 1 valence electron away from being isoelectric with helium, which is also a noble gas. Hydrogen is the only one able to do this, and it's the only thing it can do. It'll make 1 bond, and that's it. You can never put unpaired electrons or another bond or anything like that. So a bad choice for a central electron. The other 2 that I have on this question are oxygen and chlorine. So let's take a look here. Chlorine and oxygen. Now chlorine forms a -1. That means it already has 7 valence electrons. It only needs to share 1 time to get to 8, so it's only going to share 1 time. So also not a good choice for my center. Oxygen forms a -2 charge, meaning it has to share twice because it only has 6 out of 8. So I'm going to choose oxygen as my center. That makes the most sense. Okay, so here I'm going to choose oxygen, and it doesn't really matter which side I put it on. If I spin it around, it's still the same thing. That cost me 4 to draw it simple, so I have 10. I got to figure out what to do with the rest of them. So the first thing I'm going to do is go to my outsides and hydrogen. I can't do anything to hydrogen. Hydrogen's done. Chlorine has 1 bond, so it's feeling 2 electrons. It wants 8. It needs 6 more. 1, 2, 3, 4, 5, 6. Okay. And I had 10 remaining for 14 to start with. I lost 4 by drawing 2 single bonds and another 6 with those valence electrons. So therefore 6, 7, 8, 9, 10. I have 4 left, which is great because your remaining electrons you're going to put in your central atom. And so 1, 2, 3, 4, top and bottom doesn't really matter. As long as you have them paired in groups. You don't want to just draw them all willy-nilly around there because then no one will know what you're talking about. So as long as you draw them neat, you're fine. Okay, so did I use 14? I did. Let's check and make sure I used 14. So 2, 4, 6, 8, 10, 12, 14 electrons. Everyone's got an octet. Hydrogen's got a 2. Everything else has 8. This is a good drawing. Okay, let's get into some conversions. These are a big one. So I've got 50 grams of H2SO4. And what is H2SO4? Well, we know it starts with hydrogen, so it's an acid, just a side note here. And we know SO4 right here is sulfate. And if I ate and got sick, so if 8 turns into ick, then this would be sulfuric acid. That is what this is called, is sulfuric acid. So I have 50 grams of sulfuric acid. I'm going to bring my unit down like always. So that's going to be grams of H2SO4. Remember, we don't care about the 50 because we're making a conversion factor that would work for any number, including 50. So I want to go from grams to moles, which I can do. Okay. And 1 mole is equal to, well, we got to do a little math. So we're going to add together 2 hydrogens right here from the table, 2 hydrogens, 1 sulfur, and 4 oxygens. And if you add all of that up in a calculator, it's going to come out to 98.1 grams. And 50 divided by 98 is going to be somewhere about 0.5 moles. Remember, that's an approximation. So put this in the calculator, write this out, make sure you can do this yourself, and write down the actual correct answer. How many atoms are in 4 grams of calcium? Okay, this is important. This is going to be on your test, especially the advanced, is going from a measured quantity to another measured quantity. And when we're doing this, we can go from, we can go from grams, we can go from volume, we can go from particles, and all of those can go to the mole. And that's, think of this as a roadmap. So if I want to go from atoms, which is parts, okay, and what I want to go to in this case is from atoms to grams, I can't go directly from parts to grams. There's no connection for that. I have to follow the roadmap. So what I'm going to do is go from parts to mole to grams. Okay, so let's do that. Let's start with what we know, or other way around, sorry, grams to moles to parts, same thing. So I've got 4 grams of calcium. Not a lot, but let's do it. Okay. So 4 grams of calcium. Okay, whatever goes up must come down. So grams of calcium. And remember, grams can't go to another measured quantity. So really my only choice is moles of calcium. Okay. And so what I want is atoms. So I'm going to bring moles down. And I want to go to atoms, which I can do that. And so first thing I need to do is see, okay, 1 mole of calcium is going to be equal to, let's see what's 1 mole of calcium equal to? There it is, 40.078 grams, or say 40.08, close enough. Or even 40.1 grams is equal to 1 mole of calcium. And 1 mole of calcium has, or anything else, has 6.02 times 10 to the 23rd atoms. So now that I have this set up, I know that I've got 40 on the bottom, so I'm going to divide. And I've got the larger number, 6.02 times 10 to the 23rd on top. So I'm going to divide by 40.01 and multiply by 6.02 times 10 to the 23rd. So I'm going to write C video, because what I'm going to do here is I'm going to go ahead and make a quick video of me doing this in a calculator so that you can be sure you know how you're doing this. So I'm going to do 4 divided by 40.1, and then I'm going to multiply that by Avogadro's number. And so for scientific notation, it's very important that you put this in parentheses. So 6.02, and then second log. That brings up my little 10 with the chevron to the 23rd. If I needed to make a negative, which I don't, but if I did, I would make sure to use this and not this. Okay, but 10 to the 23rd. Now notice I've got 2 parentheses, one here and one here. So I am going to double close the parentheses and hit enter. And I should get, yeah, about 6.0 times 10 to the 22nd power. So look for this right here. Sometimes if your calculator is set up weird, it might even do something like 50 is like 5.0 times 10 to the 1 or something. So be careful, make sure you're looking for scientific notation at all times. Okay, and so this is going to be Just say about, but you and I, if you've been watching, you know it actually is 6.0 times 10 to the 22nd power. Okay, how many molecules are in 6.25 grams of CH4? So again, I'm going from molecules to grams. I'm going from a measured quantity to another measured quantity. And so what I want to do is set this up first. It's a lot easier if you set things up first. And so I'm going to do 6.25 grams of CH4, carbon tetrahydride, or methane, actually. And I'm going to move my unit, grams of CH4 down. Notice I'm not putting numbers at first because I don't care. I want to figure out my game plan first. And if I'm happy with it, then I'll take the time to put in numbers. I'm not instantly looking for molar masses. I might not need them. In this case, I will, but and gram, I can't go straight to molecules. That's against the rules. I have to go to moles first. It's just how it works. And then I bring down moles of CH4 to molecules. In my personally, I like to use MX as an abbreviation for molecules so I don't confuse it with moles or molarity or something like that. Molecules of CH4. Okay, and so now I'm happy with this. I'm going to go from grams to moles and moles to molecules. And so 1 mole of CH4 is just 12 plus 4 hydrogens, which are each 1. So 12 plus 4, I've got 16. Okay, and 1 mole of CH4 or anything else is composed of 6.02 times 10 to the 23rd things. Okay, so let's go ahead and get back to our calculator here. And I'm going to do clear. This is question number 8. 6.25 divided by 16 and then multiplied by Avogadro's number. So parentheses 6.02 second log. That brings up my 10 to the 23, double close, enter, and 2.35 times 10 to the 23rd. And so in here, I'm going to put about 2 point whatever. So I'm going to say about 2 times 10 to the 23rd. Okay, now we're going from moles to grams. That's a little bit easier. We're already in moles. So let's start with our given measured quantity of 0.5 moles of NaOH. Bring our unit down. And moles can go to grams of sodium hydroxide. And if we put this into a calculator, we're going to do 1 sodium, 1 oxygen, and 1 hydrogen, or 23 plus 16 plus 1, which is going to equal 40. So 1 mole is equal to 40 grams. So again, notice I am, this is 0.5 here. I'm not paying any attention to that until it's time to do my math. This conversion factor has to be a true story on its own merit, and this is a true story on its own merit. 40 grams of NaOH is equal to 1 mole of NaOH. Okay. 0.5 times 40, I think you can guess what that's going to be. So 0.5 times 40 is approximately equal to, let's say, 18 to 22 grams, although you probably know the actual answer in your head right now. How many grams of gas oxygen gas are there in 16 liters of O2? This has got a trick on it, y'all. This has got a trick. Let's circle this one. This is important. See video. Make sure you remember if I say oxygen gas, oxygen is one of my diatomics. Whoops. And what are my diatomics, you might ask? I'm glad you asked. So diatomics means that if and only if they are alone, they must be in pairs. So oxygen is one of those. So my diatomics, to figure out my diatomics, this is kind of cool. There's 7 of them. Start at 7 and draw a 7 on the periodic table. And then you are left with one more. Of course, hydrogen is always the exception to everything. So it's hiding over here. That's your 7th diatomic. And that means in their natural state, you must have 2 of these. So if I say nitrogen gas, I don't mean N, I mean N2. If I say oxygen, I mean O2. If you go diving, you never take a tank of O, it's O2. And that's why. If it's part of another compound, then the whole being diatomic thing doesn't make any difference. H2O, water, we're fine with that having 1 oxygen. So that's good. But if they're alone, make sure they're in pairs. In this question, they are alone. And so my question is, how many grams of oxygen gas are there in 16 liters of O2? So the first thing I'm going to start with is my given measured quantity. That's 16 liters of O2. So 16 liters of O2. And before I do anything else, I'm going to bring my unit down, liters of O2. And what I want is grams. Now I can't go from liters straight to grams, remember, so I can go to mole of O2, and I can bring my unit down and take 2 grams of O2. And so this one, as far as numbers, is pretty easy because 1 mole of O2 gas or any other gas in the world is going to occupy 22.4 liters. And 1 mole of O2, you could easily make the mistake of saying oxygen. Oh, that's 16 because that's what the periodic table says. But this is O2. That's 32 grams per mole. So in my calculator, I'm going to do 16 divided by 22.4 times 32. And that's going to come out to, let's just say 20 to 25 grams of O2. Okay, what is the difference between a strong and a weak electrolyte? Okay, so a strong and a weak electrolyte. So if you will recall, strong equals disassociates completely into ions. So example, sodium hydroxide is what's called a strong base and therefore is also a strong electrolyte. And so that is going to break into ions, and this is very important. Na plus and OH minus. And so if I have a solution and it breaks up, I've got a bunch of positive and negative charges just kind of floating around. And that's what can conduct electricity. Now, a weak electrolyte is much the same, except this is the important part, it partially. So it can conduct some, depends on the weak electrolyte. Some dissolve more than others or dissociate more than others, but if they don't dissociate completely, it's considered weak. Okay, an example of that would be, say, hydro. That's a monoatomic here, hydrogen and fluorine. So that becomes ick. So hydrofluoric acid is a weak acid, and that means it disassociates only partially, probably because of how strongly electronegative hydrogen is, or fluorine, sorry. Okay, define STP. This is a pretty easy one. Define STP. That is going to be standard standard temperature and pressure, and that's going to be 0 degrees Celsius. And remember, when converting Celsius to Kelvin, Kelvin equals degrees Celsius plus 273.15. So 0 degrees Celsius or 273.15 Kelvin. If you're doing math formulas, it's almost always going to need to be in Kelvin. That's just how they're set up. The whole point is Kelvin doesn't have negative numbers, so it's a lot better for math formulas. Okay, so that's our standard temperature, and our standard pressure is going to be 1 atm, which is also equal to 760 mmHg, or 101.3 kPa. So remember, all three of those are equal to each other. So we shouldn't use that color for a highlighter. So 1 atm, 760, and 101.3 are all the same, just like 0 degrees Celsius and 273.15 K are also the same. They're equivalent, just like 12 inches and 1 foot are equivalent. They're the same thing. Ooh, here we go. According to the KMT, what is the primary factor that determines the temperature of a gas? Well, this is very important. And the primary factor is temperature. Oh, wait, yeah. Determines the temperature of the gas. Okay, and that is going to be the kinetic energy. Okay, or movement of molecules. So what is the effect on particles when increasing the temperature? If you increase the temperature, they move faster and therefore have more. Now, if you have something like a balloon, it's about the best I can draw a balloon. If you start adding more and more gas to it, you're going to increase the pressure, you're going to increase all of those collisions, and that's going to expand. If it's rigid and it can expand, then you're going to increase the pressure as you increase the number of moles of gas. So, but as you increase the temperature, you get more and more collisions. There you go. What type of bonding occurs in water molecules? So this is important, in a water molecule. So N equals intra, and so that's your double, let's see. Oops. So intra is going to be covalent, and water is drawn like so. And so you have 2 single covalent bonds. So that's intra. Now for inter, this is where you have your H bond, your dipole, and your dispersion. So remember, dispersion, everybody has that. That's just a temporary dipole because the electrons are flying around everywhere. And sometimes the positive nucleus is more exposed to, say, a more negative side of a different molecule where its electrons are more on the other side. So that happens with all covalent compounds. They all have dispersion, kind of like a strip of Velcro. The more you have, the more powerful it'll be. So dipole, that just means that, dipole just means that it's a polar molecule. And water is very much polar because it has unpaired in the center. In fact, water is extremely polar. And hydrogen bonding, that is if hydrogen is bonded directly to F, O, or N, three very electronegative atoms, and we have hydrogen connected directly to oxygen. So hydrogen bonding, if it was asking for how they interact with each other or intermolecular, but again, this asks for intra. So think like introspective, what makes me me. So this would be covalent bonds would be your final answer. Okay. All right, calculate the empirical formula of iron 3 oxide. So this one's going to take a bit. This is a pretty big problem. And I'll be honest, it's probably not written all that terribly great because the empirical formula is just the lowest whole number ratio. And you can simply use the charge and you would already have the empirical formula. But in this case, it's saying calculate. So we want to see the empirical formula math. Generally, you get these with the percentages already given, but I kind of want to show you how they can both be combined. So this one, I'm going to kind of highlight this as being a very important one. So see video. Okay, but first let's go ahead and do the math on this. So the first thing I want to do, and this is going to be a big one, but it's also a very important one. The written part of your advance is built a lot on this. Okay, so first thing I want to do is iron 3 oxide. That's iron with a +3, oxygen with a -2 equals Fe2O3. Okay, and that is going to have a molar mass. Oops. This is how you write molar mass of 159.7 grams. Okay. Now I want to find out its percent composition first. So I'm going to figure out Fe2O3 divided by iron and oxygen. So each one will have its part. So that's Fe2 divided by Fe2O3. And let's just do that one first. And so, whoops, go back. So 2 irons is going to come out to 0.7 grams divided by 159.7 grams, which is going to equal 0.699 or 70%. And therefore, oxygen is going to equal the remaining 30%. If you have like 3 of them, then you may need to do this calculation more than once to have them all add up. Make sure you add up to 30. Now, if I consider 100 grams, then I can just use 70 and 30 as grams. So I'm going to do 70 grams of iron and 30 grams of oxygen. Now, again, notice I'm not saying O2. That's because this is part of a compound, and so diatomic doesn't really matter. So in this case, I'm going to divide both by their molar masses. So I'm going to divide iron by 55.8, and I'm going to divide oxygen by 16. Okay, and because it's 15.9999, so we'll just call that. Oh, I don't think that's 0.0. Okay, divide that by 16, and I get 1.25 moles. So 70 grams of iron is equal to 1.25 moles, and 30 grams of just oxygen, not O2, but oxygen, is 1.88 moles. Next, I'm going to divide. I'm going to divide by smallest, so that's 1.25 and 1.25. Anything divided by itself is 1, so that's pretty easy. 1.88 divided by 1.25 is equal to 1.88. 1.5. So in this case, our ratio, I can't say Fe10 1.5, that doesn't work. So, or 2/3. So that's also a 2/3 ratio. And so that sort of proves that it's Fe2O3, which is also how it goes together by charge. So this sort of mathematically proves it. And there we go. So make sure you know how to go back and forth on this and can do this with pretty much any compound. Okay. Okay, polar molecules, what do they have? Well, for example, again, we know water is very polar. And if you draw it like this, it sort of looks symmetrical. But let's just take a look here. Let's pick another one too. Let's say, okay, so polar molecules have an equal electron distribution. No, that's not the case. So a non-polar molecule would be, say, CO2, which we saw earlier. Okay, and notice CO2 has an even distribution. There's no unpaired in the center. So first thing you need to look for is unpaired in the center. And second, is it symmetrical? So equal distribution, no, that would be non-polar. So no permanent dipole. Okay, and so here again, no permanent dipole, but in this case, you've got a lot more negative here in the center than you do along the outside. So you have partial positive and negatives for water. So that's going to be one of the reasons it's polar. So something with no permanent dipole like CO2 is also going to be nonpolar. An uneven charge distribution. So notice here for this guy, I don't have any unpaired electrons in the center. That's good. But then I'm also not symmetrical. I've got hydrogen, 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 and chlorine. So there is going to be an uneven distribution of charge. Okay, so an uneven distribution of charge is in fact polar, and then only ionic bonds. That's polar, non-polar for ionic. That's not what we're looking for. Okay, number 18, compound. So in this case, we're already starting with percentages. So that's a little easier. Again, if I have 100 grams, then I would have 40 grams of carbon, 6.67 grams of hydrogen, and 3 grams of oxygen. Okay, and so we're going to divide these by their molar masses one at a time. And so let's see. Divided by 12, divided by 1, divided by 16. And so that's going to be 3.33. So moles, 6.67. And again, 3.33. So 53.33 divided by 16 is 3.33. 6.67 divided by 1 is itself, and then carbon. We're going to divide all of these by the smallest. So divided by okay, and that's going to give me a 1, and 6.67 divided by 3.33. That's going to be close enough to 2. So we have a 1-to-1 ratio. And so therefore CH2O. Hey, if one of them was, say, 1.5 or something like that, then I would just double all of them, but I don't have to in this case. Okay, if a compound has an empirical formula of CH2O, so sorry about the form name is fine, CH2O and a molecular mass of 180 grams per mole, then what is its molecular formula? So my empirical formula is my lowest whole number ratio, CH2O. We want to figure out what's the molar mass of CH2O because that's going to tell us what basically our lowest molar mass is. So molar mass of CH2O is going to be 12 plus 16 plus 2. And so that's going to be 30 grams per mole. Now we have a 180 grams. All right, that's what comes from here. And so we're going to divide this by our smallest. Okay, and that's going to equal 6. So therefore, we'll just CH2O. And normally we don't write the ones, but let's just go ahead and do it anyway. So if we multiply this by 6, that's going to equal C6H, and 6 times 2 is 12. And then O, 1 times 6 is 6. And so that's going to be our final answer. So you're going to end up doing quite a bit of those. So there you go. Next question. We have 250 milliliters of 0.5 molar NaOH solution. How many moles do I have? So sometimes you got to pay attention, look at it and see, okay, what formula do I need here? I've got a volume, I have a molarity. Okay, so molarity equals moles over liter. Okay, and how many moles do I have? So if I want to solve for moles, one thing I can do is rewrite this, and I'm a big fan of that. Moles equals molarity times liters. Okay, and if you don't know, there's a little trick for this. So molarity equals moles over liters. If you want to think of this as a sort of triangle, so moles is in the left-hand side, molarity. Moles is in the top and liters is in the bottom right. And basically what I can do is sort of cover up whatever it is I want to solve for. So if I wanted this case, I want to solve for moles, then I'm left with M times L. If I want to do, say, solve for liters, I cover that up and I'm left with moles divided by molarity. So kind of hard to see me covering up on your screen, but there you go. So if that helps you, cool. Okay. Now I have my molarity, my M, so I'm going to plug that into my new formula. So 0.5 times, and then remember this must be in liters, not milliliters, and there's 1,000 milliliters per liter, so 0.25. Okay, and that's my molarity, and that's my liters. Okay, and so for number 20, if I put that in my calculator, 0.25 times 0.5 is going to equal approximately 0.1 to 0.2 moles. Remember, your sheet to get credit must have the actual answer. Okay, what is the empirical formula of a compound with a molecular formula of C4H8? This is probably the easiest of the molecular empirical formula questions because I've got C4H8, and what is the lowest ratio that I can rewrite that in? The lowest ratio I can rewrite that, 4 goes into 8 twice, so I can write that as C LHH2, and that would be the same thing. Okay, next, number 22. There's actually a lot of percent compositions on here, so you should be pretty much an expert at this by the end of here. But at the end of the day, percent composition comes down to part over whole. And so what I want is, oops, sulfur divided by H2SO4. And if I add together sulfur, four oxygens and 2 hydrogens, I am going to end up with sulfur at 32.06 divided by the full molar mass of 98.08. And if I pop that into a calculator, it's going to come between 0.3 to 0.4. To get a percent, I'm going to do times 100. So therefore, it's going to be 30 to 40% for your answer. Okay, percent composition of oxygen and CO2. So in this case, we got 2 oxygens, so O2 divided by CO2, part over whole, is 12 divided by 44, which is going to equal 70 to 75, or 0.7 to 0.75 times 100 equals 70 to 75%. Excuse me. Percent composition of carbon in this is glucose, by the way. And so I'm going to do C6H12O6 divided by, whoops, wrong way. C6 divided by C6H12O6, and 6 carbons is 72 grams divided by 180.16 grams, and that is going to equal anywhere from 0.35 to 0.45, which is going to equal 35 to 45%. Okay, and so if your answers are in this range, then you're doing great. Okay, last 25 questions. There's been a lot. Okay, I'm going to go a little quicker on these because at this point we're kind of experts. So hydrogen, we've got H4 divided by CH4, and that is going to be 4 divided by 16, and that's going to come up to 0.2 to 0.3 times 100 equals 20 to 30%. All right, aluminum, Al2O3, again, Al2 over Al2O3 is going to be equal to 53.96 divided by 101.96. And ooh, they both end in 96. That's unusual. And so that is going to be somewhere about 0.5 to 0.6 times 100 equals 50 to 60%. And so make sure when you're looking at these, you know the number you expect. So 50 divided by 100, that's going to be about 0.5. So that's about the answer I would expect, is somewhere around 50. Oxygen and water. So water is mostly oxygen, and let's prove that. So I've got oxygen divided by H2O, 16 divided by 18. And this was a class example we did several times. So that equals, let's just do the real answer, 0.89, and therefore 89%. Whew. Okay, let's two. I don't think I noticed just how many of these I have. It's an important concept, but please don't take this to mean that the test is going to be 0.5% composition. Uh, it's probably could have done some other question types with this one. So K2 divided by K2CO3. Again, the hard part here is figuring out the molar masses. So 2 potassiums, 1 carbon, and 3 oxygens equals 138.21, which is going to be about 0.5 to 0.6 or 50 to 60%. Chlorine and NaCl, chlorine over NaCl, and 35.45 grams divided by 58.44 equals 0.6 to 0.65. Let's just say that. So between 60 and 65%. Last one. Percent composition of carbon in C4H10. So I got C4 divided by C4H10. And that's going to be 4 carbons is going to be 48.04 divided by 58.12. The only thing I have left is hydrogen, so those are pretty light. So this is going to be between 0.8 to 0.85 times 100 is going to be between 80 to 85%. Okay, well, now if you did all of those, you should be quite the expert on percent composition at this point. All right, let's do moles of CO2 are in 22.4 liters of CO2 gas at STP. So let's start with what we know, and that is 22.4 liters of CO2, and bring our unit down. And I honestly barely read the question before I did this because I'm always just going to take my given measure quantity and move my unit down. That's just your starting block. That's the first thing you do. After that, then I'll kind of pay more attention to what I'm doing here. And liters to moles, I can go straight there. And 1 mole of CO2 or any gas in the world occupies 22.4 liters, which makes the math pretty easy. 22.4 divided by 22.4 equals 1. So no point even doing a range for that one. Mole of CO2. Convert 2 moles of NaCl into the number of formulated. So let me slow down a bit. Let's do these. This is important that you can do multi-steps. So 2 moles of sodium chloride, NaCl. Okay, now moles to formula units. So I can do that. So formula units of NaCl and 1 mole of NaCl or anything else has 6.02 times 10 to the 23rd. And if you are not sure about how to put scientific notation in a calculator, make sure to check out question 7 of part 2 times 10 to the 23rd. So this is question 32 is going to equal about 1 to 2 times 10 to the 24th formula units of NaCl. How many grams of aluminum are in 3 moles of aluminum oxide? Okay, so this one, pay attention. This is not, this one you kind of have to make up your own step here. So I have 3 moles of aluminum oxide. So 3 moles of aluminum, Al2O3. So what I want is grams of aluminum and not grams of aluminum oxide. So this one can be a little tricky. I've got moles of aluminum oxide, and for every 1 mole of aluminum oxide, I want moles of aluminum. So for every 1 mole of aluminum oxide, I have 2 moles of aluminum. See what I did there? 1 mole of Al2O3 has 2 moles of aluminum. And then I don't move them to just moles of aluminum. And I want grams. So grams of just aluminum itself. And 1 mole of aluminum has 27 grams. So this is a 2-step. This one can be a little bit tricky. Even I kind of didn't notice it for a second there. And 3 times 2 times 27 equals about 150 to 165 grams of aluminum. So be careful that you're reading the question carefully. Occasionally something like that will pop up where you need to separate the aluminum from the aluminum oxide. Okay, number 34. How many molecules are there in 12 grams of C6H6? First thing I'm going to do, like always, is start with my given measure quantity. So I got 12 grams of C6H6. Okay, and I want to move grams of C6H6 down. And grams, pretty much my only option to go to is moles. Now I'm getting there, but what I want is molecules. So whatever goes up must come down. Moles of C6H6 to molecules of C6H6. Grams of C6H6. If I add up 6 carbons and 6 hydrogens, 78.11 grams is equal to 1 mole, and 1 mole of C6H6 or anything is 6.02 times 10 to the 23rd. So in my calculator, I'm going to do 12 divided by 78.11 and then multiply that by 6.02 times 10 to the 23rd. And if I do that, I will get approximately 9 to 9.5 times 10 to the 22nd power molecules. So again, as always, make sure you have the precise answer rounded to 2 decimal places on your answer sheet. Okay, 8 moles of water into grams. 8. We're an expert at this point. We can do this. So moles, of H2O. Moles of H2O to grams of H2O, and 1 mole is equal to 18 grams. So 8 times 18 equals 142, 145 grams of H2O. Okay, what is the volume of 0.25 molar NH solution that contains 4.5 grams of NaOH? So I'm going to have to give this a little thought. So this is molars and moles per liter. So molarity equals moles over liter. And I want to solve for liters. So I'm going to cover up liter. And I've got moles divided by molarity. So liters equals moles divided by molarity. Okay. And I've got 4.5 grams of NaOH. So I'm going to use that to find moles. So 4.5 grams NaOH. Okay, and then move grams of NaOH down to mole Okay, and 1 mole of NaOH is equal to 40 grams. So 4.5 divided by 40 equals 0.1125 moles. So that's very important. I need to know that. Okay, so for liters is going to equal moles, which is 0.1125 divided by molarity, 0.25. And if I put that into my calculator, I'm going to get 0.42, 0.5 liters. Okay, I don't need to convert it in anything. Whoops. So I can just leave that. Now, of course, your answer is going to need to be more precise. So to 2 decimal places, but you get the point. Okay, number 37. How many moles of CO2 are needed to react with 10 moles of NaOH according to the reaction NaOH plus CO2 equals NO3? Okay, so first thing, this one, I just noticed this is a mole to mole ratio, and it's not actually something that's covered on the test. So we're just going to kind of make that a note that we haven't quite gotten there yet. So not on test. Now, let's just say you're super, you want to know, right? It's actually a pretty easy question. So this is a balanced equation. So what I would do is start with my given measure quantity, which is 10 moles of NaOH. And I want to know how many moles of CO2 are needed to react. And according to this, 1 mole of NaOH reacts with 1 mole of CO2. And so this is a 1-to-1 ratio. So your answer is going to be 10. But again, we haven't done mole to mole rate relationships this year, but we will get to that as soon as we get back from the holiday break. So, okay. Let's calculate the molarity of a solution from dissolving 30 grams of NaOH into a half a liter of solution. And so molarity equals moles over liters. All right, and so first thing I need to do is convert 30 grams of NaOH moles, and 1 mole of NaOH is equal to 40 grams. And so that's going to equal 0.75 moles. Okay, and we want to divide that by liters. We don't have liters, but we have 500 milliliters. And milliliters to liters is a 1 to 1,000 ratio. So 500 divided by 1,000 is equal to 0.5 liters. Divide there, and we get between 1 to 2 molar. Okay, 39. Calculate the mass of 2.5 moles of sodium in grams. And so start with my given measure quantity, as always. 2.5 moles of sodium. Okay, and I want this not in moles, but in grams. So moles to grams. I can do that. That's pretty easy. So 1 mole of sodium is equal, according to the periodic table, to 23 grams. So this is a pretty straightforward. Put that in the calculator and you're going to get between 56 to 58 grams of Na. How many molecules of oxygen? Now, this time we said O2. That's not always going to happen. Just kind of took the questions from all kinds of places and put them together. So how many molecules of O2 are there in 4 moles of O2? Given measured quantity is 4 moles of O2. Moles of O2. And I want molecules, so I can go directly from moles to molecules. And 1 mole of O2 or anything else is 6.02 times 10 to the 23rd molecules. And 4 times 6.02 times 10 to the 23rd. I will add that to a list of things to show you. And so if I put that into a calculator, that is going to come out to about, in this one, I'll just give the actual answer to make sure that you are putting in scientific notation correctly. So you should get exactly, or at least rounded to 2.41 times 10 to the 24 molecules of O2. So this is kind of rare, but I'm giving the actual answer. But please make sure you're doing it correctly in your calculator. Okay, if I dissolve 15 grams of NaCl in enough water to make a half a liter solution, what's the molarity of the solution? Okay, so molarity equals moles over liter. I don't need to rewrite this. I just need to figure out the moles and the liters. As usual, I'm given grams and not moles. Got to do the work. So 15 grams of NaCl. I'm going to convert that by grams of NaCl to moles, and 1 sodium and 1 chlorine together is 58.44 grams for 1 mole. And so that's going to be 0.257 moles of NaCl divided by liters, which I have 500 milliliters. And really, you can just move the decimal place over 3. You don't necessarily have to always put this in a calculator. So 1, 2, 3. Okay, and that's going to equal 0.5 liters. And so that is going to be 0.5 to 0.6. Percent composition is looks like percent composition popped back up. Where'd you come from? I thought we had done with you. So Na2 divided by Na2SO4. This does bring up a good point. In a test, usually the questions aren't grouped together like they are in a review, where you kind of, like when we did percent composition, it got repetitive. But be careful in the test so you're actually reading each question, because they're usually not the same question types, one right after the other. So anyway, in this one, that's going to be 2 sodiums. That's going to be like 46 divided by Na2SO4, which is 142 grams, which should be about 0.3 to 0.4 or 30 to 40%. Okay, this one's a little more important. So this is an empirical formula of a compound with 27.8% nitrogen, 72% magnesium. And so what I'm going to do here is assume 100 grams. Okay. And so that means I'm going to start with nitrogen. I'm going to start with 27.8 grams of nitrogen. And for magnesium, I'm going to start with 72.2 grams of magnesium. Now, if there's any question, I should have put a whole ton of them on here. It would be something like this. So I did add a few. This is actually changed from last year. So please make sure you know how to do these. These are very important. So nitrogen is 14.01 according to the periodic table, and magnesium is 24.31 grams per mole according to the periodic table. So if I do this, I get 1.99, and here I get 2.97. Okay, and that makes a pretty short work of this one. Okay, and so this is very obviously a 2 to 3 ratio. But remember, when you do something like this, when you do an empirical formula, this is kind of seems a little long. In this case, it feels weird and it seems a little long, but you are still supposed to divide by the smallest. And that's going to equal 1 to 1.5. I can't do a 1 to 1.5 ratio, so I'm going to change that to 2/3, which is the actual ratio. So sometimes if you go back and look at the iron oxide one we did, dividing by the smallest really does kind of clear it up. It's not quite as obvious. In this case, it is obvious, but it doesn't matter. You still need to divide by the smallest. And then in this case, 1 to 1.5 is actually a 2 to 3 ratio. And so we can do positive comes first. So you would not write and then magnesium. Remember, positive magnesium comes first. So that's going to be Mg, and that's got a 3, and N, which we came up with a 2. And so that's going to be your answer. Now for the, all right, home stretch, last page. How many grams of KCl are in 0.25 moles of KCl? So let's start there. 0.25 moles of KCl, and move our unit down. And it wants grams, which we can go straight there, so that's cool. And 1 mole is equal to 74.55 grams. Now, notice the reason I'm writing this formula is I don't have to worry about, do I need to multiply or divide? If I take my unit and I bring my unit down every time and then convert to whatever it is I can convert to. In moles, I can go to grams, liters, particles, whatever. If I'm in one of those, I can go to mole. But if I write it like this, I always know if I need to multiply or divide. I don't have to worry about it. And in this case, 0.7455 divided by 0.25. So you should expect an answer right around the range of 17 to 19 grams of KCl. Remember to post your answer to 2 decimal places. All right, 45. If 250 milliliters of 0.5 molar solution is diluted, what is the new molarity? Okay, this is an M1V1 equals M2V2 kind of situation. And I want the new molarity, so that means I want M2. So I'm going to divide both sides by V2, and that's going to give me M2 equals M1V1 divided by M2 divided by V2. Okay, now it's just kind of a plug and chug sort of thing. So my M1, that's going to be, now be careful. First time I did this, I wrote 4 moles. I just saw 4, I messed up. So I had to go in and redo this one. but it was 0.4, not 4, times 250 milliliters, which you should be just kind of look at this and immediately see, okay, that's 0.25 liters. So 0.25 liters divided by my V2, which is 1 liter. So 1, that's easy enough. And so that basically equals 0.1 divided by 1, which equals, well, can't really put a range for this, so we'll just put the answer 0.1 molar. (46) A solution contains 20 grams of NaCl dissolved in 300 milliliters of solution. What is the molarity? Okay, so molarity equals moles over liter. No need to rewrite this whole thing, but I do need to convert 20 grams to moles. So 20 grams of NaCl. Move grams of NaCl down to mole. And 1 mole of NaCl is equal to 58.4 grams, which equals 20 divided by 58.4 equals 0.34 moles. And then 300 milliliters is equal to 0.3 milliliter, or sorry, 0.3 liters. So that means your answer is going to be about 1 to 1.3. I keep wanting to write milliliters, liters. So if your answer is between 1 and 1.3, congratulations, you are doing fantastic. And we are almost done. 3 more questions. Okay, a solution of H2SO4 is 0.2 molars. How many moles are there in a 500 milliliter solution? Okay, so molarity equals moles over liter. And so the question is asking how many moles. So let's solve for moles. If I cover up moles, I'm left with molarity times liter. So moles equals M times L. Okay, and so my molarity is 2. So 2 times, and my number of liters is 0.5 liters. And 2 times 0.5 is 1. So 1 mole of H2SO4. Percent okay, I need to next year take some of these out, but all right. So let's just do it anyway. C2 divided by C2H6. All right, part over whole. So that's 24 divided by 30, which is 0.8, which is 80%. Not even going to do a round on that one. Okay, how many grams are needed to make 2 liters of a 0.25 molar solution? Okay, that's cool. So this one is a bit reversed. This one's helpful. So how many grams are needed to make 2 liters of a 0.5 molar solution? So molarity equals moles over liters. To get to grams, it would be helpful to have moles. So moles equals M times L. And my molarity is 2 times, wait, no, it's not. That's my number of liters. So my molarity, and this is why I rewrite it. This is great. I rewrite it because I want to make sure that I don't put the wrong thing in there. Now, in this case, 1 thing times another wouldn't actually have mattered if I had crossed it, but it would matter a lot if I had one in the numerator versus denominator or something like that. Okay, so in this case, my molarity is 0.25 times my liters of 2.0. And what's 2 times 0.25, you may ask, and that is going to be 0.5 moles. Now, remember, if you are doing this in a multiple choice, that's almost for sure going to be one of the answers, but that isn't the answer. It's getting there. But what we want is grams, not grams, moles. So mole to grams, and 1 mole of K2SO4 is equal to 174 grams. And so therefore, your answer is going to be between 85 to, or let's say 86 to 88 grams. And so that's going to be your actual answer. I think the very first time I did this question, I accidentally stopped at 0.5 moles because it is a very easy mistake to make, not reading the question. A lot of wrong answers come from that. So try not to let that happen. Now that you've finished, be sure to watch the video of me doing the problems. Well, if you're here, then you already did that. So yay. If you have any questions, let me know. And thanks for sticking with me. I'll see you soon.